This is intimidating.
I hate this one. I really don't like it.
Yeah.
Don't tell me that this room more like this than this is when Buffer came. So we are like. Seems that yeah, that's good. A lot of students are here, which is
Great.
Hello, everyone. Welcome to this joint colloquium between the physics department, Malga in computer science, and INFN at Genova. So for physics, this is the final colloquium of the year. Well, we'll start again in October, of the academic year. We are very happy to have Jesse Thaler as a speaker. So let me try and introduce Jesse. Jesse's career is defined by phases. So he started as a PhD student at Harvard under the supervision of Nima Arkaniamet, working on physics beyond the standard model and these sort of things. Then he started, while starting his first postdoc at Berkeley and then becoming faculty at MIT, the LHC turned up, and so he started thinking about ways that models of new physics can be seen or not seen in the data. And sort of that led into his first phase transition. So he started thinking about more QCD, jet physics, and that's how we met in the past. And not happy with that, he had another phase transition around 2020, so around COVID time, 2018, 2019. Well, thanks to 2 PhD students, he was convinced that artificial intelligence and machine learning were a topic that was coming and it was like worth investigating. So that's like it's a message for students. You can convince your own advisors to change field. So since then, he's become a main character in this business of artificial intelligence and physics, so that he was the founding director of an MIT institute, which is the Institute for Artificial Intelligence and Fundamental Interactions. So we're very happy to have him here today, telling us about Centaur science. Thank you, Jess.
Great. Thanks so much, Simone. I should say that my transition into the world of machine learning, I was very much a curmudgeon. And part of that is that I was trying to protect my citation counts with Simone. And so actually, Simone, our top cited paper together for both of us comes from the pre-machine learning world. And when these 2 graduate students came to my office saying that they thought that machine learning was going to revolutionize particle physics, I said, no, I'm worried about my Inspire record. So we can't go in that direction. I've since been converted from a curmudgeon to an evangelist for physics at the, science at the intersection of physics and artificial intelligence. Currently, I am on sabbatical in Paris, so that's why you have these 2 symbols added to my affiliations. It's been an opportunity to be my own graduate student and change my own mind based on me having a conversation between myself and AI, so you'll see a little bit about that in this talk today. Really want to emphasize this point that it's early career talent that's been driving this interdisciplinary work at the intersection of AI and physics. And I'm seeing this firsthand at the institute that I direct, where we're trying to bring together AI experts and physics experts viewing artificial intelligence as a pathway to scientific insight, but also physics intelligence as a way of driving AI innovation. And as I said, it's really junior people who are driving this. And some of the people who you'll be seeing in this talk are our I+Phi postdoctoral fellows, specific people, Siddharth Mishra Sharma, who is one of our first cohorts of postdoctoral fellows, who's now splitting his time between academia at Boston University, but also a research scientist at commercial venture, Anthropic. And then 2 other I+Phi fellows, Thomas Harvey and Sam Brightoni, who one's from the more formal theory world, one's from the more experimental particle physics world, but we've all been having a really fun time collaborating together. If you're interested in learning more, you are not invited to our I+Phi summer school and workshop. Not invited because we are oversubscribed by a factor of something like 6 to 8. So you can get on the very, very long waiting list, but you won't get in. Here you can see my former student Rekop Gambier and current student Sean Benevedes is very happy to be learning about this intersection of physics and AI. But keep a lookout. We've been doing this every summer. And if you want to learn more, you can come join us in Boston to learn from experts at this interdisciplinary intersection. So the main thesis of this colloquium is a kind of lesson that I've learned personally from this collision, if you like, between physics and AI. So of course, coming from a particle physics perspective, thinking about things smashing together and studying the debris. And what's been the debris from this collision of physics and AI? One has been a realization that to meet the standards of scientific rigor and performance, we need to teach machines to think like a physicist. Part of my reluctance to go into machine learning was a sense that it was black boxy, you couldn't understand uncertainties, didn't satisfy physical principles. But over time, I've realized that you can actually embed physics concepts into machine learning architectures. And one that I was discussing with folks over lunch was the idea of symmetries. In physics, we have space-time symmetries and other types of symmetries. And you can build neural network architectures that respect those known structures from the physical world. So this is the part of the talk that makes me feel really good. I get to talk about how physics has inspired different types of AI advances. The flip side, which is more difficult, given my training, to appreciate, is that if we want to fully capitalize on AI technologies, we also need to teach physicists to think more like a machine. And certainly as part of my PhD training, I was doing pencil and paper calculations, doing quantum field theory calculations in a traditional way, but thinking about computational complexity, algorithmic reasoning, search and optimization, that was not part of my training, but you'll see it featured heavily in this talk today, and I really see these strategies as a way of pushing the forefront of our understanding of physics. And this idea of combining these two messages, thinking like a physicist and thinking like a machine, that's why you get this title of this talk, Centaur Science. The centaur, of course, is the mythical Greek creature that is half human, half beast. And you can ask in this analogy, like, which is it the machine learning or the physics part that's the human versus the beast part? Okay, but this idea of combining physics and computation and information theory has a long, long history. It's well before we had machine learning. For example, statistical mechanics can be viewed both as the study of thermodynamic systems, but also has an information theoretic framing, which I'll remind you of later on in this talk. Lattice gauge theory is putting quantum field theory on a computer, and that process of translating a physical system into a computational one drove advances in supercomputing. Quantum computers are another example where, of course, quantum mechanics is a physical phenomena, but quantum computing is changing the way that we think of processing information. And so there's been this tight dialogue for decades or centuries between these areas. And the challenge in the machine learning era is to find the right balance. What's the balance between physics concepts versus more computer science concepts? And I was giving a talk like this one at the University of Wisconsin in Madison, and another enthusiast for AI+Physics is Kyle Kramer, and he sent me this cartoon when he saw the title of my talk, Centaur Science. And this cartoon I now feel an obligation to keep showing because it really captures in a pretty funny way the challenge that I'm facing. So this is the New Yorker cartoon of the Centaur scale, okay? On one end, you have not enough horse. You're not taking advantage of, let's say, AI technologies. On the other side, you have too much horse, too much smooth optimization. And finding this right balance, the right amount of horse, that's the balance that I'm trying to strike in my research. And especially when you're talking about things like agentic AI systems and the idea that you might replace scientists with AI, I don't believe that that's what's going to happen. I think we're going to have something more like a synthesis of different methods, both synthesis of different methods, but also the synthesis of different ways of thinking, both human ways of thinking and computer ways of thinking. So just to show you one example of this, as I mentioned, I'm on sabbatical. And even though I direct this AI Institute, I have no responsibilities at the moment. But I feel a responsibility to highlight the interim director, Mike Williams, and his research while he is holding the fort and dealing with funding issues at the National Science Foundation. I feel like I should at least highlight one of the things that he's done. And Mike is an experimentalist on the LHCb collaboration, but he's really interested in understanding the physics of AI. And one of the problems that he and his collaborators studied was this funny phenomena in machine learning where you have a system that's trying to learn some mathematical equations, can't figure it out, can't figure it out, can't figure it out, and you leave the computer on overnight, and suddenly it has an epiphany. And this is known in the machine learning literature as grokking. It's this kind of notion that when you train longer than you think you should, you go from a kind of overfitting the data to actually getting good generalization. And he was able to show that this actually, in a certain context, is literally a phase transition. So this is the internal dynamics of a neural network, an internal latent space, where you have kind of like a gas of information that suddenly turns into kind of like a crystal of organized knowledge. And you can actually show that the training dynamics is one that drives you into this very ordered state. And again, we would, as physicists, think about this as being a kind of phase transition. And he was able to use a language that's familiar to theoretical physicists, that of effective field theories, to understand kind of where this dynamics comes from. Now that you know that as part of the learning dynamics, you can get internal organized structured states inside of a neural network, you can now say, well, what about problems that are not simple math? So this is a modular arithmetic, basically addition modulo 60. But what if you take a more complicated system and ask about the type of internal representations for that complicated system? And he's a member of the LHCb collaboration, studies nuclear physics. And so we wanted to take data from nuclear isotopes and try to understand whether the data tables of nuclear isotopes had a similar type of internal structure. And what he and collaborators found is that the internal dynamics, the DNA of nuclear physics, if you like, is literally like a double helix in a latent space, where these gray lines, the hydrogen bonds from DNA, correspond to neutron and proton configurations that are in the lowest ground state. And so he's actually able to understand nuclear data tables in this new machine-learned representation that turns out to be more accurate than human-derived models. And so this is an example of taking advantage both of understanding learning dynamics on the one side, using physics concepts, and then using the emergent behavior of computational systems to understand physical systems. And this kind of two-way dialogue is something that I really find quite interesting. So for the remainder of this colloquium, I first want to kind of talk to my former self and remind myself, why is it that actually machine learning is quite familiar to us as physicists, and thinking about machine learning through the lens of physics, and then take you through two examples from my research of seeing this kind of Centaur science in action. One example will be relating properties of quantum chromodynamics, what I studied with Simone, relating that to information theory. And one is a sabbatical project that's been really a lot of fun that's taken me well outside my comfort zone. Okay, so first let me kind of translate machine learning jargon into physics jargon. And one of the things you immediately encounter when you face the literature on AI/ML is kind of two kind of overblown statements. One, you'll hear people say, AI is totally transforming society. It's transformative technology. And then you'll hear people say, no, machine learning, it's just numerical optimization, nothing special. And the answer is actually just both. So both are true, and both are changing the scientific enterprise. And the way that I like to think about it is a little bit of a different scrambling of these concepts, that I like to think about the difference between direct AI/ML. So this is where you as the scientist controls exactly what you're trying to optimize. And in the context of my research on the Large Hadron Collider, this allows scientific investigations of very high dimensional spaces. And in terms of buzzwords, this is the idea of simulation-based inference, that you can take a simulation of particle physics data, compare it to real data, and try to infer the fundamental knowledge from that comparison. And that's been able to be facilitated by direct AI/ML techniques, where you bake into your loss function exactly that goal of doing scientific inference. Another thing that you might want to do, though, is indirect AI/ML. And this is capitalizing on emergent behaviors in computational systems. So if you've heard of foundation models, these are models that are trained on vast amounts of data, and then you use that knowledge, whatever that is, to do downstream tasks. Not really clear what the foundation model is exactly learning. Or agentic AI systems, which you'll see more in the last part of this talk, where you're basically using the fact that language is very rich. There's structures inside of language that allow you to, for example, have an agent do coding for you, or write a paper for you, or write a talk for you. And that's something that we don't really understand where that emergent behavior comes from, but something that you might want to try to capitalize on in a scientific context. Both direct and indirect AI/ML is changing what it means to do things that we physicists have done for a long time. It's changing the way that you would design, build, and operate experiments. So this is a picture from the next accelerator that will happen in the United States, the Electron-Ion Collider, where already the optimization of the detectors are starting to happen using AI techniques. And indeed, it seems like the way that you're going to operate the experiment and train graduate students on how to use the experiment will take advantage of AI. AI is changing the way that we're performing and reporting measurements. As I mentioned, we're doing now things in very high dimensional spaces. And even though this plot from the ATLAS experiment to the LHC looks like a bunch of histograms, that's only because our human brains can't contemplate the fact that we've done actually a 24-dimensional measurement. And so we have to project it down onto histograms just to visualize it. But actually, this is a case of making a 24-dimensional, unbinned, corrected for all the detector effects measurement. Again, something that your brain can't comprehend, but nevertheless, the machine is able to process that high-dimensional information. And even the search for new physics is now being done using various anomaly detection strategies, so looking for rare or bizarre features in data sets, able to break free of the specific model building that I was trained how to do when I was a graduate student, and now looking very generically for deviations from predictions. This is an example from the CMS experiment where one search essentially covers the territory that before you had kind of dozens of searches. So this is what's happening on the experimental side of particle physics. But even on the theory side, AI is changing what it means to make theory predictions. And so you've probably heard of deepfake images or deepfake videos where you're making hallucinated images that are trying to mimic data on the internet. It turns out that the identical technology you can use for lattice gauge theory, where you do deepfake gauge field configurations, and you have hallucinated gluons, And you might say, how could you possibly do rigorous science if you're using hallucinating AIs? And the answer is, yes, it's a hallucination, but it's a hallucination that tells you exactly what the probability of sampling that hallucination was, such you can correct that answer to compare it to the known quantum field theory result and do a correction factor such that at the end of the day, your result is as rigorous as traditional ways of doing lattice gauge theory. And this promises to actually accelerate theory calculations beyond what you would be able to do with traditional optimization strategies. And AI is also changing like what it means to be a physicist or be a theoretical physicist. And these bars are representing a AI reasoning benchmark called the theoretical physics benchmark task. And these bars correspond to first undergraduate problem sets, graduate problem sets, and then research grade problems. And when this paper first came out, none of the AI systems could solve research grade problems. And now you're hitting close to 50% ability to solve very, very hard problems. I challenge you to go to this TP bench and just see how difficult some of these problems are that AI is now solving. And the capabilities have now crossed a threshold where otherwise reasonable people are now using AI as a collaborator. And so my colleague at IFI, Matt Schwartz, wrote a paper this past January with a title that seems reasonable. It says, Resummation of the C-parameter Sudakov shoulder using effective field theory. But Matt himself never typed anything directly into the paper. He did none of the calculations directly. He was just coordinating his AI research assistant, Claude Opus 4.5, to write this paper. And this really challenges the notion of what does it mean to be a scientist, what it means to be an author. And it's something that we're trying to wrestle with in our community, and many communities are trying to figure out what to do with these systems. And I'll have a little bit of an answer at the end of this talk of what I think. But at the end of the day, both direct applications of AI and indirect applications of AI, it's just machine learning, just numerical optimization in response to data. And the examples that I'm going to be showing in this talk are, at some level, they're not even going to use neural networks, actually. It's going to be a type of AI, if you'd like, that's taking advantage of computational abilities, but in a way that maybe gets away from some of the breathless enthusiasm that you might have heard. So it's more as a talk than you might have expected, given its title. But for example, training data to a machine learning practitioner, a physicist would just say, I'm doing Monte Carlo phase space integration. So it's a little bit funny to think about training on data from like celebrity images, and really what you're doing is sampling the phase space of beautiful people. Like what dimensionality do beautiful people live in? That's kind of an interesting thing, but that's what you're doing with up to corrections, 1 over square root of n corrections, that a physicist knows you need to make that as small as possible if you want to have a good estimate of your integral. The thing that you're trying to optimize is called a loss function, and it's the same symbol, L, that to a physicist is the Lagrangian. So what I would teach to a student at MIT about classical mechanics and the Euler-Lagrange equations and how to do the equivalent of F equals ma, that appears in machine learning as trying to find a functional derivative of a loss function. And once you know that, actually, it helps you build new loss functions that can do tasks of interest to you. In the machine learning world, we often talk about neural networks, but really all these are flexible functions that you have a lot of parameters that you can move around. Not so different from a Fourier transform in that sense. And in this talk, we're going to have functions that have physics baked directly into it. Yes, there'll be parameters that we're going to move around, but we can bake physics knowledge in. I mentioned already symmetries, and that's going to appear in the last part of this talk. And then even the optimizers themselves, you've probably heard of gradient descent. Gradient descent, to a physicist, is just Newtonian dynamics of an overdamped oscillator. So when you can think about your parameters as being like a ball rolling around, when the inertia term is negligible and you just have friction, then solving overdamped oscillators is basically solving the dynamics of gradient descent. And then you might say, is gradient descent a good or a bad optimizer? Well, you can think physically about whether there might be other ways of navigating a lost landscape that could give you better solutions. And so the examples that I'm going to be showing in this talk are ones that take advantage of these 4 ingredients, but maybe in a way that's different than you might be expecting. Okay, so for the interest of time, I'm going to skip over some of the work of my collaborators, fun stuff, you can ask me about it offline. But what we're seeing is this rise of Centaur scientists who are synthesizing physics intelligence and artificial intelligence, taking aspects of both, And you'll see this in the two examples from my research that I'll be going through next. Okay, so this next part of the talk is about confronting thorny challenges in theoretical physics through a frame of optimization. And one of the things that I want to maybe start off with is a reaction to this idea of thinking like a machine and whether that's a good idea or not if you're doing science. And there's an inspiring and infuriating at the same time paper by David Hogg and Soledad Villar with the title, "Is Machine Learning Good or Bad for the Natural Sciences?" That is basically kind of highlighting some of the issues that we face when trying to combine physics and AI, or science in general and AI. So let me just read out the beginning of the abstract. Machine learning methods are having a huge impact across all the sciences. However, machine learning has a strong ontology in which only the data exist, and a strong epistemology in which a model is considered good if it performs well on held-out training data. These philosophies are in strong conflict with both standard practices and key philosophies in the natural sciences. So unless you've recently taken a course on the philosophy of science, this probably is a bunch of gobbledygook jargon. So let me try to translate it to you, roughly speaking. And this is very much a cartoon, extreme view of the fields. There's actually more nuance in this. But roughly speaking, what Hogg and Villar are saying is that in the machine learning community, what exists is the data, and success looks like you can accurately model that data. So if the data is all the text on the internet, and if you can do next word prediction for the next word that might appear in a sentence that could have come from the internet, then you declare success. Again, an oversimplification, but that's the cartoon version of the machine learning community. In physics and the natural sciences more generally, we actually think that other things exist. It's not just the data, it's also underlying latent structures. We think that quantum fields exist. We think that equations of motion exist. We think that coupling constants exist. We think that particles exist. And what it means to be successful is a core understanding of the underlying dynamics. And we're actually willing to sacrifice accurate modeling if we can gain insight. That's basically what they're saying. So in picture form, here are these sprays of particles at the Large Hadron Collider called jets, which I love to study, and I study with Simone. This is the data. But this is not the only information that I care about as a particle physicist. I care about things like quarks and gluons. And these sprays of particles, these jets, are manifestations of underlying quarks and gluons. They're described by the theory of quantum chromodynamics that comes from the standard model of particle physics. Here's the standard model of particle physics in pie chart form with particles like the Higgs boson discovered in 2012. The Higgs boson is not in the data. We only infer it from the data. But we think of the Higgs boson as existing and actually having scientific value. And so what Hogg and Villar are basically saying is that you have two communities that have a different standard of what success looks like. And given my title of Centaur Science, you might imagine that my answer to their concern is, no, we're going to do both things. We're going to try to synthesize these two different perspectives. So imagine that you could have a generative model that is a way of generating synthetic data that could mimic all the collisions that happen at the LHC. What if you could generate synthetic LHC collisions that were indistinguishable in some statistical sense from real LHC data? In that case, would you consider this to have scientific value? And according to Hogg and Villar, this conflicts with the epistemology of the natural sciences. That is, mimicry by itself does not correspond to understanding. On the flip side, what if you could generate synthetic LHC collisions based entirely on first principles quantum field theory calculations? That would be amazing if you could do it. That's a long-term, like very, very long-term aspiration of the field. Nowhere near being able to do that at all. What is the Centaur scientist view? The Centaur scientist view is, well, let's do both. Let's combine models of LHC data for the full phase space and combine them with first principles predictions when they're available and try to interpolate between these two extreme viewpoints, trying to take advantage of the abilities both of the physics side but also on the computing side. So for experts, what I'll be describing now is a version of what experts would call parton shower matrix element matching, but we're going to do it through a framework of optimization. In cartoon form, we have the too much human, the general purpose event generator that can make arbitrary LHC predictions but at low accuracy. So in the particle physics community, we call these parton showers. If you're not in our community, you can think about these as somewhat trustable AI hallucinations, with apologies to the parton shower people. That's one way of thinking about what they are, roughly speaking. On the other hand, we have these super sleek, specialized QCD calculations that can make high accuracy LHC predictions for specific observables. So you invest a huge amount of time doing these heroic, amazing calculations, but they can only make predictions for a narrow range of quantities. And you like to synthesize these together to get a general purpose event generator for the LHC that will provably reproduce any specialized QCD calculation. And that would be synthesizing these two different viewpoints. This might sound really difficult. How would you possibly going to put these things together? Well, based on what I told you earlier in the talk, you need the 4 ingredients. You need to have training data, a loss function, a learnable function, and an optimizer. And here, the training data is itself theory calculations. So we often think about training data as like, you take pictures of people, or you have text on the internet. But these are going to be precision calculations. That's going to be my training data. That's the thing I'm going to anchor my predictions to. My loss function will be based actually on information theory or statistical mechanics. My learnable function will not be a neural network. It will be something that a physicist will like. It will look like a Boltzmann factor. And then there's some efficient nonlinear solver as the optimizer to actually find the configuration that minimizes the loss as defined. So in the backup slides, I have the derivation of this if people are interested. But let me just tell you what the final answer is and connect it to physics knowledge. So when all the dust is settled, the result of this optimization looks like, to what a physicist looks like, the Boltzmann factor, the e to the minus beta e. This is the thing that appears in thermodynamic systems. And Boltzmann told us a long time ago that this is the solution to the question of how do you have a maximum entropy or maximum uncertainty solution subject to constraints on quantities. In this particular case, we're dealing with a thermodynamic system that has a constraint on the average energy. The beta is a Lagrange multiplier in the physics jargon to impose a constraint on the average energy. And this completely generalizes, and Boltzmann knew this, that anytime you have something that you want to enforce, you can have an exponential of that thing that you want to enforce, and you'll make sure that your answer satisfies that constraint. So in the particle physics context that I just explained, the thing that I want to enforce is my precious theory calculation. That's the thing that I want to make sure is true. So the generalization is that I'm going to have an exponential that has various constrained quantities that I've done precision calculations for, and then I'm going to adjust the Lagrange multiplier, adjust the temperature, if you'd like, in order to match those theory calculations. And unlike in statistical mechanics, where we talk about having, or quantum statistical mechanics, where we have microstates that are all equally populated, here we have to have a prior. And you can think about that as the parton shower or the AI hallucination or a prior in the Bayesian sense of kind of starting expectation for what things will look like. And so you have this combined factor, the piece of it that is your best guess before you did the theory calculation, and then the tail part is the imposing of the constraints from the theory calculation. So if you can perform precision QCD calculations of moment constraints, that's constraints on average quantities, then you can improve prior predictions with learned Lagrange multipliers. And this is a machine learning problem. It doesn't look like a machine learning problem. It looks like a stat mech problem. And this reframing in this language turns out to be kind of helpful. Now, given the years on this, Boltzmann did this in the 1800s. You might say, why are we only talking about this in this century? Like, what was stopping people from making this connection? And so it's actually kind of interesting to go back to kind of the way that we normally think about QCD and think about like how this might relate to what I just told you on the previous slide. So this is now just for the experts. And at the end, for the non-experts, you should just smile and say, okay, you physicists, theoretical physicists, I'm glad you found a connection between different disciplines. But that's all you should know. For the experts, here's a random QCD calculation computed with a Caesar-style approach, where you can ask, does this look like a prior times exponential of something? Well, yes, we have an exponential of the radiator function. The radiator function itself has various factors in it, in particular the logarithm of some observable. And we have the radiator is proportional to the log squared. And we're going to somehow relate this to this information theoretic perspective. So to a QCD theorist, this is just some simplified next to leading logarithmic calculation. To a machine learning practitioner, this is an opportunity for this neurosymbolic learning. There's kind of some funny special functions in there. But if you're taking this kind of Centaur science perspective, and now this is just pure jargon for the experts, To a Centaur scientist, the Sudakov form factor is a kind of Boltzmann factor where the cusp anomalous dimension is like a Lagrange multiplier that enforces a constraint on the second logarithmic moment of the distribution. And, okay, that's just jargon. The amazing thing is, to my knowledge, logarithmic moments, the second logarithmic moment, this L squared, had never been computed ever in the QCD literature. And yet, from this information theoretic perspective, that should be the first thing that you compute. And maybe to put this in a perspective that makes it maybe more obvious, if someone gives you a Gaussian distribution, what do you compute? You compute the mean and the variance. Here I'm saying that we've never computed the variance of the Sudakov form factor before, which is kind of amazing that we had this blind spot, and I can tell you in the backup slides why we had that blind spot. But at the end of the day, you now have something that you can start to attach machine learning jargon to. This idea of a foundation model, taking a bucket of information, putting it together and synthesizing it into this thing that's supposed to be able to represent your knowledge about the field. Only this is a foundation model built on theoretical calculations. So it's fully trustable to the extent that you trust the theory calculations. You ingest a bunch of precision inputs, you tack them on to hallucinations or parton showers, and then you output something that now an experimentalist can use and do inference on. You need to choose what constraints you want to use. Based on the work with the two students that Simona mentioned, Patrick Kamitsky and Eric Metodiev, we developed this way of systematically studying the space of collider physics data using these fun graphs. And these graphs correspond to things that you can make measurements of at the LHC. And then with Ben Asi, Kyle Lee, and Stefan Höcke, who are all like real QCD people, we were able to take this calculations and then ingest it into a framework where you can start off with a hallucination. So this gray line corresponds to a hallucination in some 200-dimensional space. I don't know how to visualize a 200-dimensional space, so all I can say is it's bad on the top and good on the bottom. So you start with a bad hallucination. And then as you start adding more and more of these precision constraints, you get better and better mapping of the data that you're trying to model. And then with these graphs correspond to partial information about QCD. But then you can try to extrapolate, what we would typically do with the foundation model, take my training data and extrapolate it to a new domain. In this case, the new domain could correspond to new graphs that go beyond what we've done the calculation for. And in graph theory, at least around Boston and MIT, there's a very famous American movie, Good Will Hunting, where Matt Damon draws random graphs on the board. These correspond to observables that were not in the training data set. And then in this panel here, you can see that you would have good transfer learning from what you calculated to what you haven't yet calculated, a transfer of knowledge from one domain to another, if you'd like. And this is now facilitated by this different perspective of how you would synthesize theoretical information into a machine learning framework. Okay, so this was a technical part of the talk, but hopefully you get the sense of a different way of thinking about machine learning, synthesizing knowledge from that we trust, the physics side, and combining it with computational structures to get a unified whole. So Centaur science kind of continuing this tradition of relating properties of physical systems to concepts in computation and information theory. So in the last part of the talk, I want to talk about my own experience on sabbatical. So on sabbatical in Paris, a full year away from MIT, a full year where I've been able to explore emerging AI technologies. And what I've decided is that being a Centaur scientist myself means capitalizing on these technologies while still insisting on scientific rigor and robustness. And one of the things that I've struggled with on sabbatical is, what does it mean to do robust discovery science with AI? So in the back of my mind, I have this idea that sometime in the coming decade, let's say, we're going to have the next run of the Large Hadron Collider, the high luminosity LHC, and there's going to be some cool new thing that's seen using an AI technique. And now you need to convince the scientific community that you've actually made a discovery. And how will you do that? How will you convince the community? I already mentioned in the case of lattice gauge theory certain guarantees of exactness that you can say even if the AI hallucinates, you can nevertheless correct it to the right answer. So that's one way of doing it. Another way that people are thinking about it is with explicit verification, symbolic engines, or things like automatic theorem proving software that you can write a code that can show whether a math statement is true or false if it compiles correctly. with my student, Sean Benavides, who just defended his PhD thesis last month. We're thinking about statistical verification and making sure that you have, even if you're using AI, calibrated confidence intervals. So when you say I've made a 5 sigma discovery, you know exactly what 5 sigma itself means. And so what I'm going to be showing now is a case study about how my own thinking has evolved, but we're going to do it in a purely theoretical context. So this is going to be new theoretical physics, but we're going to do it with optimization, and we're going to have to figure out how we convince ourselves that we found something new. Okay. So for people who know me, this next slide is going to be shocking. As Simona said, I've gone through various phase transitions in my career. I don't know whether this is a phase transition or just me having a hobby. Okay, but like I tend to like to live in the real world. I tend to like to talk to my experimental friends. I tend to like to live in 3+1 dimensions. I tend to like to have things like units and scales and dimensional analysis. And somehow I find myself on sabbatical studying 2-dimensional conformal field theories that have none of that. So 2-dimensional conformal field theories, 2 dimensions, 1 space, 1 time. Conformal, scale invariant, so there's no notion of like a ruler. it's all scaling symmetric. Field theories, okay, quantum field theories, I like that. This is a highly constrained mathematical framework that we know a lot about, though I don't know much about it. And so somehow on sabbatical, being in Paris, where there's a lot of CFT experts, decided, oh, I'm going to study 2-dimensional conformal field theories using machine learning. Okay, we're going to put things in Euclidean space, put it on a torus, so we have 2 dimensions. This is my universe, okay? And I'm on sabbatical. When I wake up in the morning, my grad students and postdocs are still asleep in Boston, so I need someone to talk to. So, okay, I'll talk to Claude. Claude is both a research assistant and a little bit of a therapist or a life coach. It's kind of fun. Okay, and I'm going to pose a research question to Claude. And Claude, I'm using Claude because Siddharth Mishra Sharma, who I mentioned before, he works at Anthropic, and he gave me a bucket of Claude credits to use. And so, great, I got to burn those up. Okay. So ask a research question to Claude. So please identify a 2-dimensional conformal field theory with central charge in the range of 1 to 1.15. So in a conformal field theory, central charge is like the number of degrees of freedom. So C equals 1 is 1 free boson. So C is like 1.1 is like a little bit of an interacting free boson, if you want to think about it kind of like that. So please identify a CFT with that property. And it gives me an answer. It tells me that the Z5 parafermion CFT has a central charge of 8/7, which is 1.143. That's within my window. We declare success. We're just 4 decades too late. So this is already very well known. And this demonstrates how agentic AI systems are really good at doing literature search. And so as long as you ask it nicely, it will not hallucinate citations. It will give you beautiful bibliographies. Just ask nicely and verify. And it's quite useful in that sense. Okay, but that's not a very good research question for sabbatical. I don't want to just do a glorified Google search. Okay, great. Let me revise my question. Please identify a 2D CFT with central charge in the range of 1 to 1.14. Okay, great. You've narrowed the window to exclude that theory I had before. And Claude says, to my knowledge, there is no known unitary 2D CFT that has that property. And this is the space of known CFTs, given in terms of the central charge, that's roughly the number of degrees of freedom, and the spectral gap. So in quantum mechanics, you have the ground state and the first excited state. You can think about this as being the energy level of the first excited state, roughly speaking, except for this is a conformal theory. There's no units. So it's an energy, but it's a dimensionless energy. And the free boson with different kind of geometries corresponds to any spectral gap you want. That's that purple band here. And then we have 3 theories. This is the Z5 parafermion CFT. That is the n equals 1 minimal model with m equals 5. And I forget what that dot is, but it's some CFT. And nothing else is there. It's known that you can't go above that black dashed line. There's nothing up here. That yellow band has been excluded by my collaborators, Liam Fitzpatrick and Wei Li. Wei Li just defended his PhD thesis. A heroic calculation for Wei to rule out that little slice. So you can work really, really hard and have barely anything to show for it, unfortunately, in this very difficult theoretical physics problem. Are there any other CFTs in this range? Could I convince the experts? So in addition to Liam and Wei, Nathan Benjamin is an expert in this area. Could I convince my collaborators that I found something? Could I convince myself? would I be willing to go to a colloquium in Genoa and present these results, right? And that's the question, is like, how would you trust an AI-generated answer to this question? That's the sabbatical project that I've been working on. Okay, so going back to earlier in the talk, I said there's indirect AI and there's direct AI. Indirect AI, you might just ask really nicely to Claude, hey, could you just think about it a little bit more and just come up with a new theory that doesn't exist in the literature? Just ask nicely, and it refuses. Okay, so it refuses to hallucinate, which is good. It knows that I don't like to be fooled, and it's learned over time, don't hallucinate when Jesse's around. Also, like, be very careful with semicolons and em dashes. It gets me upset. And instead, it says maybe there's some deep reason that one doesn't exist, or maybe there's some new construction that we could try to come up with. Or you could try to use direct AI/ML strategies. And when I first started this project, I thought, geez, there must be a bunch of theoretical physicists who have tried to solve this problem. And the answer is, not really. I mean, there is a literature, a bunch of different techniques. That is a very short bibliography, because it's really, really hard. And for people who know about this research area, the reason why it's hard is that there's a huge industry of what's called the dual conformal bootstrap. And there we can make rigorous results. You're not really using, I mean, you also are using numerical optimization, but not a machine learning style one. And there, a huge industry, beautiful results have been obtained in that area. Here we're trying to do what's called the primal approach, trying to rule in a new theory. And that's just hard, really hard. And yet I've decided that this is going to be my sabbatical passion project, and maybe AI will help me. This problem is so hard that I'm going to retreat. I'm not going to try to solve the full problem in general. I'm going to try to solve an even more restricted version of the problem. So experts would know this is called the modular bootstrap, and I'll try to do my best to explain to you what this is. And I myself am not an expert, so I'm roughly speaking at the same level as you all were if I translate myself back to September of last year. So this is a necessary but not sufficient condition for one of these conformal field theories to exist. And it's an example of a more general bootstrap philosophy of defining theoretical objects by consistency conditions. So you write down a bunch of equations, and if you can find solutions to those equations, then you've declared success. And that feels very much like a machine learning problem. A machine should be able to manipulate numbers around until you find answers, and that's basically what we're going to try to do. So this is a funny theory. We have the data of a CFT. So we have the energy levels of the system, roughly speaking, in quantum mechanics, and the angular momentum, the spin. So we have dimensions and spin. Dimension, but without units, so it's kind of funny. And then this is like a quantum system, so we have dimensions and spin and degeneracy. And so we say, okay, how many states do I have in my theory that have spin 2 and energy 3.5, and that should be an integer. So degeneracy is an integer. Spin, in this case, is a bosonic theory, so it's an integer. And dimension is bounded by spin. And just like we did with Boltzmann's approach to statistical mechanics with that e to the minus beta e, you have the same thing here. We have a sum over energy levels, if you'd like, to define the partition function. That's the sum over e to the minus beta e for all the energy levels of the system, roughly speaking. And that partition function is a function of the geometry of your torus. That's the generalization of temperature. The tensor charge of my theory, and then the operator dimensions, spin, and degeneracies. What it means for a theory to be conformal is that it has this funny relationship where the geometry of this donut, this tau, is a complex number. And if the partition function for tau and the partition function for -1 over tau are the same, then I declare success. Okay? So essentially, cartoon-wise, the machine is going to jiggle around these orange dots until some function that's not a neural network, it's a physics object, a partition function, satisfies this quantity. The particular orange dots here are from a known model, and I'm going to try to find new ones. That is, new dots that satisfy that condition. That's the problem. When I first started this problem, I'm like, a week, 2 weeks, no problem. Instead, it was my whole sabbatical. Okay, so based on what I said earlier on in this talk, we have a choice. We can either think like a machine or think like a physicist or do both. Let's start off by thinking like a machine and have our 4 ingredients again: training data, loss function, learnable function, optimizer. To a machine learning practitioner, The modular bootstrap is just a version of self-supervised learning. Training data. In this case, the training data is just doing a Monte Carlo integral over all the shapes of the donut. So I want to integrate over all donut shapes, and I can do that by sampling example donuts. So that's my training data, just different donuts. My loss function is going to enforce this modular invariance. So I took the equation from the previous slide, such that if z of tau equals z of minus 1 over tau, this thing will be 0. I throw it inside of a square. That's the mean squared error loss function. If I make that 0, I declare success. My learnable function is not a neural network. It's a partition function with this data. And I'm going to move the location of those orange dots around to try to make that loss be 0. And my optimizer, I'll just do some gradient descent. Again, clearly easy. No problem. Week, 2 weeks max, no problem. So what works for this particular problem is that, thankfully, Monte Carlo integration works and physics works. Partition functions are awesome. Monte Carlo integration works. What doesn't work is highly informative. This loss function is bad, and this optimizer is bad, like really bad. And essentially, a huge amount of the time was figuring out how to wrestle with this problem and coming up with, how do you come up with a loss function that actually satisfies the condition that I want, and how do I make an optimizer that actually can solve to make this loss as small as possible? So if I just do this, this approach fails dramatically at finding anything close to physical. So we're done thinking like a machine. Now we want to think like a physicist. And amusingly, the biggest insight that I got into a theoretical physics problem, the biggest insight into a theoretical physics problem was thinking like an experimental physicist. Because an experimental physicist would say, you know, well, what do you mean that these two things are equal? What's the uncertainty on that? What's your confidence interval? It's not the prediction, it's the uncertainty. So we would never use, if you're an experimentalist, you would never use mean squared error. You would instead use something that's like chi-squared. So if you think like an experimental physicist and you have the uncertainties on your loss function, you need to have chi-squared. That means you need to have the uncertainty in the denominator. So what's happening is I move tau around. The numerator spans, this is on a logarithmic scale, spans 20 orders of magnitude. And essentially, the machine would just cheat. It would find solutions that would bury the bad behavior into some terms in the loss function that were small, but the uncertainties would be similarly small, such that I actually wouldn't get a good result. If instead I use this experimentalist physicist loss function, then the distribution is a chi-squared distribution. That is, it's like I have Gaussian noise that I'm modeling. And this is completely wild, because this is purely theoretical data. And yet theoretical data with the best estimate of the uncertainties gives you something that has like a chi-squared behavior, such that 0 in the log, that's 1. So that chi-squared per degree of freedom of 1 really corresponds to something that works. So this is the distributions in a known CFT. If I can make my loss basically be 1, then I declare success. So this sounds great, right? So I've thought like an experimental physicist. I put an uncertainty in the denominator. And then you say, well, what is the uncertainty on your theory calculation? My collaborators didn't know, so I now needed to ask AI. And unfortunately, I've lost the transcript of my conversation with Claude, so this is a reenactment. So I needed a robust method to quantify uncertainties. So this is the reenactment. So hey, Claude, we previously discussed a strategy for taking a known conformal field theory with central charge of 1, deforming its partition function to mimic the Carty scaling behavior of a CFT with C greater than 1 in order to estimate uncertainties associated with truncating the primary spectrum. Can you remind me of that formula and where it first appeared in the literature? So that's a bunch of jargon for you. That was a 48-hour conversation that I was having with Claude trying to figure this out. We figured it out. Where did it first appear in the literature? Ah, yes, here's the formula that we use. A similar construction appears in Benjamin, Collier, Fitzpatrick, Maloney, and Perlmutter. Oh, wait. Benjamin and Fitzpatrick are my collaborators. They did not realize that their own paper had the solution to the question that we needed to answer. And this is an example of agentic AI systems finding connections in the literature that even the authors of the paper didn't realize that their method could generalize to a new problem. They were trying to solve some other problem, and yet collaborating with Claude helped me identify a way of solving the problem of interest. Okay, so now we have a loss function, and the lesson from this is uncertainties matter. And so when anytime you now see a machine learning problem and you want to annoy the speaker, You just say, hey, what about the uncertainties on your machine learning? And they better have a good answer. And for this problem, now I do have a good answer. Now, what about the optimizer? And for this, we had to think like think like a mathematical physicist. So this is with Sam and Thomas, who I mentioned before, as well as a string theorist, Andre Lucas, who's at Oxford. And here, I'm not going to go into any detail on this, but we had to think about the geometry of the loss landscape and think about moving about on geodesics in my loss landscape. And so we introduced this kind of interesting quasi-second order method that does better than stochastic gradient descent. And roughly speaking, to a physics audience, you can explain why you need to do this in the following way. If I have a vector, say a covariant vector, its derivative is a contravariant vector. So if I'm doing gradient descent and shifting a parameter by a derivative, the indices don't match. So when I teach special relativity, I tell my students, you gotta make sure the indices match. How do you get a lower index and an upper index to connect? You have a metric. And so that's not what you're doing, just putting in a metric on your optimizer. It just happens to be that this metric is expensive to compute, and we have some GitHub repo that has a more efficient way of estimating what that metric is. And once you do that, you go from having really bad solutions, this does not look like a CFT, to something that definitely looks like a CFT. Okay, so now we can bring all these ingredients together and update the space of candidate two-dimensional conformal field theories. So remember, this is a necessary but not sufficient constraint. So the dots that I'm going to show you are candidates, but I can't tell you whether they are or not real CFTs. We can talk more about that in Q&A if you'd like. This is a combination of dealing with formal theoretical physicists, with machine learning folks, collaborating with an agentic AI system, and doing coding lovingly by hand. I coded everything with Mathematica. Sadly, when I started doing this project, the coding skills of Claude with Mathematica weren't quite good enough, and it was hallucinating too many functions, so I gave up and did it all by hand. We have these known theories, and now there's a question of what does it look like? Does it look like the space of candidate CFTs? And again, you can think about this from the perspective of my collaborators. Like, what do they expect to see? And they said, oh, Jesse, you're just going to fill the whole space. You're going to find theories everywhere. No problem. And that is not what we found. We found theories most everywhere. We reproduced that line at 1. That's good. And then we have this hole. We have an obstruction. There is something that's stopping this optimizer from finding examples. I don't know what this corresponds to. I do know that my collaborators are surprised. I do know, and I can show you in the backup slides if you want, that I went through enough tests to convince them that we should publish this and that I should be able to talk about it to you today. But it's surprising. It's not what you would have expected. Remember, my collaborators said the bounds that you're going to get are going to be like the wedges. So that's what they found, excluding wedges. This is not excluding a wedge. This is excluding some kind of region. There's an obstruction to finding theories there. I don't know how we would have gotten this result without AI/ML methods. That we had to use this direct construction, this optimizer, this loss function. That's the only way I know how to address this thing. We had to reframe this bootstrap problem in this optimization language. At the same time, I don't know how to do it without indirect AI/ML. If I didn't have Claude to talk through this issue of uncertainties, I don't know how we would have made any progress. So this is the power of AI for scientific reasoning. That's one half of the Centaur. But the other half is I also don't know how we would have gotten this result without input from the physics community. And having experts who could tell me what problems are relevant, that's really important to have physics expertise in the room. Developing a new optimization algorithm based on physics intuition of geodesics and raising and lowering indices, that was important. And then also this experimental insight of pursuing statistical robustness even in a purely theoretical setting, that was also really important to get this result. So just putting this thing together, we're advancing, in this case, theoretical physics through the Centaur-style merging of physical reasoning and computational algorithms. And then the interesting question to you, as an audience is, well, to what extent would you be convinced by this story? What else would you want to see to be convinced that we've either found or excluded theories? And that's also the thing that we're going to have to wrestle with, not just for this imaginary world of two-dimensional conformal field theories, but when we're deploying AI systems for scientific problems more generally. So summarizing things before we go to Q&A. So in this collision between AI and physics, AI is transforming physics research, but the fundamental aspects or foundational aspects of AI have a language that's familiar to physicists. And so hopefully you feel a little bit less intimidated by machine learning if you're not using these tools, And if you are using these tools as a physicist, you feel empowered that there's actually a physics backing behind them. I then told you 2 examples from my research, one based on optimization to synthesize a lot of theory calculations into one unified whole, and then another one where we're wrestling with this question of discovery, and where without AI/ML, we wouldn't have been able to make scientific progress, or at least I don't know how to make scientific progress. So with that, let me just reemphasize this idea of this collision between fields, progress being driven by early career talent, and looking forward to taking questions from you all. Thanks very much.
Thank you, Jesse. Questions? Whoa. It's a long way. So our director, not the...
Take a rest now, yeah? Okay. So I'm not in the field. However, you mentioned that you map everything into an optimization problem.
Yeah.
Which means exploring a landscape to search for the best minimum.
Yes.
How do you know, since you mentioned LBFGS, which is a local minimizer, all steps, steepest descent, how do you know that this is the best minimum? Because usually landscapes have a huge number of minima from wherever, so you may go in the wrong place.
Yeah, good. So the answer is different for the 2 examples of my talk. So the beautiful thing about information theory, and the second part, is that you can prove that it's a convex optimization problem. So that one's just proven, again, anyone who's ever done maximum entry problems knows this already. This is very well known. Convex optimization, LBFGS does amazingly well. That's fine. This bottom one, we don't know. And this is what drove my collaborators crazy. So I'm trying to identify solutions. If I find one, I found a solution. What if I don't find one? What does that mean? Maybe my optimizer's bad. And yes, that's a deep concern that you could have. And so to convince myself that this is robust, you end up doing a variety of cross-checks and variations, but ultimately you don't have a proof. And that is something that we have to figure out how to address. So what's running on my laptop right now is I took the results from my collaborator here, that yellow band, and this morning I said, you know what? I'm just going to push this problem to the max. So the yellow band, this type of optimization is fully provable. When you exclude something, it's definitely gone. And so I asked Claude to read Wei's PhD thesis, reproduce that yellow band, and then try to throw as much compute at it as you possibly can to see if you could lower it. And the hope is that, well, the real hope was that by the end of this colloquium, I would be able to show you that actually the yellow band decreased like that. That is not true. Instead, what Claude told me is that, sorry, your laptop overheated, and we need to adjust the CPU usage. So it had to throttle it back to make sure that it didn't burst into flames. But that's the type of thing that you would do. And so that's the problem anytime you do optimization, is that you don't know whether you found an answer. Luckily, this is a problem that has both a primal and a dual framing. And closing that gap is the thing that we would need to do to convince ourselves that it was real. But this is the problem that we always have in AI, and I don't have a solution to it other than cross-checks that you would do as a physicist. Yeah.
Thank you very much.
More questions? I need an assistant.
Thanks, Simone. So I have a question on this example. So
yeah.
First, I don't understand, why do you call it a learning problem? I mean, do you have a test set? Is it really a learning, or it's just optimization? If it's just optimization, it has nothing to do with AI. This is what I don't understand.
Yeah. So this is
all these ingredients are just like regression or something like statistical inference?
Yep,
okay.
Absolutely. So a machine learning person would call this self-supervised learning, but self-supervised learning is just numerical optimization. So what is aspects of it that are taking advantage of the specific capabilities of AI? That's the question.
The difference is whether you test on unseen data or not. It's not the self-supervised. Self-supervised learning may well be machine learning. So you test it on unseen data and you look how it generalizes. So, is this what you're doing?
Okay. It's not at all obvious by the way that I do it, but I'm really using the whole machine learning pipeline. So let's give examples of things that help in the machine learning pipeline. So one thing that really helps for optimization in modern machine learning is overparameterization. And so you might say, wait, how is your partition function overparameterized? Well, you can actually check that there's a null space, a kind of moduli space, and the fact that you have that moduli space, that's one of the reasons why you can find an answer. I'm doing stochastic optimization. If I do it with deterministic optimization, I don't find things that work. So the S and SGD generalized here, that's important. And then, and this is really crucial, is that this plot that I made here is made with a held out training data set. And you're like, wait, what held out training data set? So what I do is I stochastically sample over donuts, Then separately, when I evaluate the loss, I have a new set of donuts that I test on. So I'm doing the same kind of test validation. So I'm really treating it as if it's a machine learning problem. And it's very instructive to see what happens wrong when I break any of those things. So if I don't have overparameterized, I can't find answers. If I don't do stochastic learning, I get stuck in local minima. And if I don't do that separate validation set, then I get overconfident in the answer. And so you're right, it's just numerical optimization. And yet, because I know the language of machine learning, it helps me from avoiding pitfalls that you would have if you didn't know about those aspects. But at some level, yeah, it's just numerical optimization. And with not even with neural networks, just with partition functions. But that ML perspective was absolutely essential for being able to actually gain confidence in the results.
The other comment is a Theo's comment.
Yeah.
So, okay, it was good that you identified that the mean square error is not enough, that you need uncertainty, but then in the chi-square, in the denominator, you put a theoretical uncertainty, which is a big concern. Because, I mean, this sigma in the chi-square is really the statistical uncertainty of your variable. Theoretical uncertainty is like truncation of a series, is not a statistical uncertainty. So how do you expect that this should work? Should have any meaning? This is what we do all the time with nuisance parameters for parameterizing theoretical uncertainties. It's a big problem that we know. But here, why do you expect that this should work?
So when I saw this distribution, that it was chi-square distributed empirically, I was blown away. Because I said, this is theoretical data. It's not a statistical uncertainty. How is it that you actually have a problem where it's, as you said, a truncation uncertainty, doesn't really have a statistical meaning? Why does it satisfy that property? And the answer appears to be that in the space of conformal field theories, essentially you have some kind of, random matrices type of behavior in those particular constructions, and that's why you end up getting something of this form. So what I can do is I can empirically calibrate it on those 3 orange dots and show that it has that behavior, but I am baffled that it behaves like this. But it turns out to be essential for finding solutions to have at least an estimate of what the uncertainty is.
So if that error was the truncation of the perturbative expansion in a perturbative calculation, it's not clear that you expect the same.
And the key difference here is that I really do have a notion of a distribution or an ensemble. I have an ensemble of tau values. So it's not just one number. Any individual term here will have some value, but it's the ensemble of different taus. When I do something like a perturbative expansion, you can ask, well, what's the equivalent of doing a random sampling? And indeed, if you think that sometimes you go up, sometimes you go below, and you have some kind of central limidity theorem behavior, you kind of expect something Gaussian-ish. I didn't expect it to be that good. And it's not perfect. I mean, it's not like you see a depletion here and expansion there. But that perspective ended up being a useful one, even though, as you say, you have no formal reason to believe that should be at all a random variable. And it's not a random variable. It's theoretical data. It just happens to be random enough to gain confidence in the answers. I'm not sure if you're satisfied by that, but that's the empirical observation. Yeah. Have I ask the question again?
If you have done the same calculation also with multi-agent systems or local systems specifically trained apart from Claude?
Yes, so one thing to emphasize in both the examples that I showed you, the final scientific result was just regular old numerical optimization. The reasoning and teaching myself about conformal field theories, that was happening through the agentic systems. So in terms of multi-agent behavior, yes, I have, but not in this context. So this calculation, the results here were done lovingly coded by hand in Mathematica with insights from Claude, but I ended up hand coding it. And this talk, everything that's in this talk, I dragged the images in and put them in there and typed it in, right? But I gave a presentation about AI and academic publishing to a bunch of academic publishers, and I launched a multi-agent system to create the slide deck, do the research, review the slide deck, critique it, and then using that to create a slide deck that had very little human input into it. And that multi-agent interactions and the type of amazing high quality of the slide deck that it generated blew me away. For these problems, when I try to do multi-agent type of thing or try to have a dialogue, if the answer isn't known in the literature, I find that I just go into some crazy thing. So when I did this uncertainty thing, trying to launch multiple agents didn't really help. It was a human AI dialogue rather than an AI dialogue that ended up being useful. But we'll see, as these things evolve, maybe it will end up being that a combination of human AI, those dialogues might be useful. I'll give you one more example. A collaborator of mine, his name is Ben Nachman, and he and I have been collaborating together for many years. And we decided that we were going to try a collaboration where it's me and my Claude and him and his Claude. And then the Claudes would argue back with each other. And so it's really fascinating. It's the same underlying AI system, but because it's being driven by different prompts, you end up getting different responses. And that dialogue of human-human, AI-human, AI-human, AI-AI is actually quite fascinating. We don't have any papers on that yet, but it's been interesting to see that dynamics at play when you have multiple agents.
The interaction gives an evolution trajectory, and they are different, so that the different instances of Claude, they behave differently.
They behave differently, and then the question is whether it will ever converge, as opposed to just diverging and them kind of going in some kind of cycle of confusion. And so that's the thing that we're trying to figure out. But
physics should make them converge.
You would hope that the physics would make it converge. But it's really interesting because, oftentimes, as I showed earlier on with this kind of phases, like a phase change in learning, depending on what hyperparameters you choose, my Claude will choose one set of hyperparameters, get one result. Ben's Claude will choose a different hyperparameters, get a different result. And they have different scientific conclusions that they would draw, but it's just changes of hyperparameters. And so this is a case where, you hopefully with enough iterations, you end up finding what the right answer is, but it's complicated in the same way that academic literature is complicated and people can disagree until you get a more complete picture. So.
Yet you are using LLM engine, or as you are studying new engines based on physics?
Ask the question again?
If you are using only LLM engines, or you are developing a physics engine?
Good. So the question was, am I using just out-of-the-box LLMs, or am I trying to develop my own physics agents? So it happens to be that the forefront models are so good out of the box that any attempt that I make to try to guide its development has not been very useful. Something that has been interesting is been using a forefront model to generate instructions for a cheaper model. And so you generate, here's how to think about the problem using a fancy agent, and then you hand it to a cheaper agent to try to implement that strategy. That's been interesting. But ultimately, I've been, this is a version of the bitter lesson, frustrated by how much Claude Opus 4.7 knows about my own field, and how little I've been able to, in some sense, improve its behavior with specific scaffolding around it. It seems like the generic scaffolding is already, like the commercial scaffolding is already something that's too good. And it's harder for me as a scientist to put additional scaffolding around it, but it is possible to take cheaper LLMs with additional scaffolding and use that to mimic the behavior of a more expensive system. That does seem to be possible.
Okay, maybe we have time for one more question, maybe from, I was going to say for a student, but it's also Elena.
Thank you.
Yeah.
Have you tried also other, for example, you cited Claude,
Yeah.
research agent.
Yeah.
Can you compare his results in respect to others?
Yeah. So
This could be interesting.
yeah, so one of the challenges that I found in doing these comparisons is that, so there's two systems that I've used extensively. So one is ChatGPT and the other one is Claude. MIT actually gives access to, I don't know, like 40 different models. But one of the challenges is how do you do something that's in a reproducible way to understand the generic behavior of these systems? So my anecdotal experience is that for the science problems that I'm doing, ChatGPT gives more accurate answers than Claude does. However, I find Claude to be much more useful as a research assistant because it goes off on these kind of crazy tangents and tells me things about the literature. It just kind of spontaneously mentions things that end up being useful. And so ChatGPT somehow in its default mode wants to give you the right answer and just give you that and stop. Claude is kind of rambling and tells you about all these things, and that actually has ended up being more useful for me as a research assistant. So there's another project that I'm working on where Claude was useless in terms of actually proving something, but it generated a bunch of failed proofs, and the failed proofs used aspects of the statistics literature that I didn't know about. The proofs are all garbage. It was really bad, and yet I learned something by its strategy. And somehow Claude kind of exposes more about what it's doing in the internals, and that's useful for me. But if I want a factually correct thing, and I want to do it in one shot, I find that ChatGPT, whatever the latest version, does better for that aspect. But it's hard to generalize, yeah.
Okay, final question.
Last one.
Okay. I'm one of these experimentalists that
Yeah.
are providing you data. So sometimes we start thinking more like even engineers instead of physicists. So my my question is probably trivial, but have you ever estimated how much, let's say, energy, computing power, CPU power, all these kind of things you need? I mean, cost.
Yeah.
For example, the solution of this problem.
Yeah.
So
it's dizzying. So I can give you two examples, and both of these examples I think point to what the future is and what physicists can do to help. So this plot that you see here was roughly me coding Mathematica and running it for 2 weeks with a fancy optimizer. And this machine, you know, my sabbatical laptop, was drawing a ton of power, you know, like catching on fire. I mean, not really, but like getting really, really hot. The fans are blowing full blast. A postdoc at MIT took the paper that we wrote and my GitHub repo. It redid all my code in PyTorch. It fixed some of the memory management issues and was able to reproduce this in less than an hour. So this is a case where if you now go back to my Mathematica code and you ask why was it so inefficient, what it was doing, it was caching a lot of information. The memory usage was outrageous. The way it was taking derivatives was super inefficient. It wasn't reusing information. So this is a case where my bad human coding was super inefficient. I was wasting a lot of energy, and it took an AI to go up and clean up it completely. So that's one story I can tell you, and this is a case where actually one can hope that using these agentic systems could actually make us build more efficient systems. And as I mentioned, I was trying to expand this yellow band and redo the calculation. The fact that it was able to diagnose for me that I was using too much CPU usage, I was hitting the thermal limit, and it was giving me advice about how to moderate, that's telling you that it actually knows a lot more about computing than I do, and that could help us make things more efficient from a more engineering perspective. Then you can ask the question for this thing, like what was the cost of that? What was the cost of using Claude to come up with that insight? And I think it's probably in the thousands of dollars. I don't know because Siddharth Mishra Sharma gave me a bunch of Claude credits. I didn't really know kind of how, it wasn't Claude credits, it was a Claude Max subscription, so you don't even get to see how expensive it was. That was probably a few $1,000s. And This does not feel scalable if we want every single scientist to be using these tools on a regular basis. Okay, so what hope do we have? Are we going to use up all the energy, all the water? What's going to happen? So I mentioned my student, his PhD thesis. The day after his PhD thesis defense, there was another student who's part of this AI institute that I direct. And what he developed was a non-transformer large language model that had the same capacity as a large language model, but instead of having quadratic runtime in the number of tokens, it had linear runtime in the number of tokens. This is a very cool PhD thesis. So the way that transformers work is you're kind of doing this self-attention mechanism, and essentially you're correlating every token with every other one. And so I think Claude Max allows you to have 1 million tokens. So that means 1 million squared connections. That's very expensive. What the student was able to develop on a toy problem is something that had the capacity to ingest all of Wikipedia, but only needed to read Wikipedia once instead of having to correlate all pairs of words. That's way more dramatically inexpensive, and it has much better scaling properties. That's an example of a physicist, so he's a condensed matter theorist, and he actually developed this idea using ideas from entanglement entropy, like a physics concept, and saying how much information is being correlated between the first half and the second half of a context window, and able to use that to develop this new type of architecture, which is more efficient computationally. He has no idea how to train this thing, so there's still work to be done before this becomes a viable product, but it's an example of physicists thinking about things from scaling perspective, or even in this case, almost like a moral perspective, the moral imperative to make your computation as cheap as possible, and coming up with solutions using physics insights. And so that gives me some hope that maybe we won't completely destroy the planet by using these techniques, but it requires an active engagement, and I would hope that physicists would be at the forefront of trying to drive that more efficient use of these technologies.
Okay, so as usual, we have refreshment outside, so I really encourage students to come and talk to Jesse. Jesse's around the whole of today. So thank you very much again for this colloquium.
Thank you.
Sorry, but it's a complicated time.
Thanks
for coming, and thanks for the talk.
It
was really nice. Unfortunately, I couldn't join for dinner. It's a complicated time, but...
families.